Good morning, everyone. This is the first lecture of NLP, and in today's lecture, we are going to learn about basic text processing. I'm Arghya. I'm a student at York University, and my email is arghyak@yorku.ca. If you have any questions, please feel free to drop me an email. Now, let's get started. In today's lecture, we are going to first learn about why NLP, what is the purpose of NLP, what is the use of NLP, and the evolution of NLP. Then we are going to focus on regular expressions. After that, we're going to learn about text normalization, and finally, about edit distances. So why NLP? NLP stands for Natural Language Processing. It is a subfield of artificial intelligence that assists computers with understanding human language. Utilizing NLP, machines can understand unstructured online information, so we can gain significant insights. As computer technology advances past their artificial requirements, companies are searching for better approaches to exploit. A sharp increase in computing speed and capability has led to a new and highly intelligent software system, some of which are prepared to supplant or augment human services. NLP is important because it helps resolve ambiguity in language and adds useful numeric structure to the data for many downstream applications, such as speech recognition or text analytics or fake news detection. Now, what is the evolution of NLP? While natural language processing isn't a new science, the technology is rapidly advancing thanks to an increased interest in human to machine communications, plus an availability of big data, powerful computing, and enhanced algorithms. As a human, you may speak and write in English, Spanish, or Chinese, but a computer's native language, known as machine code or machine language, is largely incomprehensible to most people. At your device's lowest level, communication occurs not with words, but through millions of zeros and ones that produce logical actions. Indeed, programmers used punch cards to communicate with the first computer 70 years ago. This manual and arduous process was understood by a relatively small number of people. Now you can say, Alexa, I like this song, and a device playing music in your home will lower the volume and reply, okay, rating saved, in a human-like voice. Then it adapts its algorithm to play that song, and others like it. The next time you listen to that music station, let's take a closer look at that interaction. Your device activated when it heard you speak, understood the unspoken intent in the comment, executed an action, and provided feedback in a well-formed English sentence, all in a space of about 5 seconds. The complete interaction was made possible by NLP, along with other AI elements such as machine learning and deep learning. Now, let's look at an example of a NLP system. This dialogue above is from Eliza, an early natural language processing system that could carry on a limited conversation with a user by imitating the responses of a Rokerian psychotherapist. This system was designed in 1966, that is way back. Eliza is a surprisingly simple program that uses pattern matching to recognize phrases like I need X and translate them into suitable outputs like what would it mean to you if you got X. This simple technique succeeds in this domain because Eliza doesn't actually need to know anything to mimic a Rogerian psychotherapist. As the author notes, this is one of the few dialogue genres where listeners can act as if they know nothing of the world. Eliza's mimicry of human conversation was remarkably successful. Many people who interacted with Eliza came to believe that it really understood them and their problem. Many continue to believe in Eliza's capabilities even after the program's operation was explained to them. And even today, such chatbots are a fun diversion. Of course, modern conversational systems are much more than a diversion. They can answer questions, book flights, or find restaurants, functions for which they rely on a much more sophisticated understanding of the user's intent. As we will see in the next lectures, nonetheless, the simple pattern-based methods that powered Eliza and other chatbots play a crucial role in natural language processing. We will begin with the most important tool for describing text patterns, the regular expression. Regular expressions can be used to specify strings we might want to extract from a document for transforming. I need X in Eliza above. To define strings like $200 or $24.9 for extracting tables of prices from a document. This practical language is used in every computer language, word processor, and text processing tools like the Unix tools grep and Emacs. For example, how can you search the words wood chunk, wood chunks with, or a wood chunk with a capital W, or wood chunks with a capital W from a corpus of text? Formally, regular expression is an algebraic notation for characterizing a set of strings. They are particularly useful for searching in text, which when we have a pattern to search for and a corpus of text to search through. A regular expression search function will search through the entire corpus, returning all texts that match the pattern. The corpus can be a single document or a collection. For example, the Unix command line tool grep takes a regular expression and returns every line of the input document that matches the function. A search can be designed to return every match on a line if there are more than one or just the first match. Regular expressions come in many variants. Using an online regular expression tester is a handy way to test your expressions and explore these variations. Regular expressions are case sensitive. That is, a lowercase s is distinct from the uppercase s. This means that the pattern wood chunks with a small w will not match the string wood chunks with a capital W. We can solve this problem with the use of square braces. The string of characters inside the braces specifies a disjunction of characters to match. For example, the pattern W and a higher case W matches the pattern containing either the lowercase w or the uppercase W. That is, the wood chunk and the wood chunk, both of them will get matched. The regular expression starting from 1 to 0 specifies any single digit. So using this expression, we can match any digit from 0 to 1, 0 to 9. While such classes of characters as digits or letters are important building blocks in expressions, they can get awkward. For example, if we want to specify all the characters in the English alphabet, then it will be a huge expression, right? So in cases where there is a well-defined sequence associated with a set of characters, the brackets can be used with a dash to specify any one of the characters in a range. The pattern 2-5 specifies any one of the characters, that is 2, 3, 4, or 5. The pattern B-G specifies one of the characters B, C, D, E, F, or G. Thus, the first pattern in this slide from A to Z will specify any uppercase character. And as you can see from the example, the first character is D, which is a capitalized character, gets matched. And the second example is will match any lowercase letter, and it gets matched. Now, generally, in these examples, we're matching the first appearance of any such character, but they can be extended to match any one or all of the characters that the regular expression matches with the corpus of characters. But for simplicity, we'll just use a regular expression to match the first occurrence of any of the characters in the regular expression. Similarly, in the third example, 0-9, any single digit is matched. That is, in the example, the character 1 it gets matched. The square braces can also be used to specify what a character cannot be by the use of the special character caret. If the caret symbol is the first symbol after the open square brace, the resulting pattern is negated. For example, the pattern caret A matches any single character, including special characters, except for A. Now note that this is only true when the caret is the first symbol after the open square braces. If it occurs anywhere else, it usually stands for a caret. So in the first example, it will not match any uppercase letter. That is, as you can see in the example, Y, which is the first occurrence of a lowercase letter, gets matched. In the second example, neither S or not the small lower version of S gets matched. And in the third example, this E and then the caret, this particular symbol is not matched. So the first character, that is L in the example, gets matched. In the last example, as you can see, the caret appears outside the braces. This regulates a pattern to be matched. That is the pattern A caret B. It will match as you can see in the example, the A caret B this particular sequence of symbols gets matched. Now more disjunctions can be used. For example, if you are searching in a text of corpus for the word wood chunk or groundhog, so this pipeline character can also be used. Thus, this groundhog, pipeline, wood chunk, this particular set of symbols will match any word in the corpus of text which has the word wood chunk or groundhog in it. Thus, the second example, yours, pipeline, mine, will match any word which is yours or mine in the corpus of the text. In the third example, A, B, or C will get matched, the character. It is equivalent to mentioning it in the square brackets A, B, C. So the left hand side, A, pipeline B, pipeline C, is equivalent to mentioning bracket open A, B, C, bracket closed as a regular expression. In the fourth and the final example, the groundhog and the wood chunk, it will get matched whether the W or the G is in lowercase or the small or in uppercase. Now let us focus on few particularly interesting regular expression symbols. That is the question mark, the star, the plus, and the dot. The star is known as the Kleene star, and the dot is and the plus is known as the Kleene plus. How can we talk about optional elements? like an optional S in wood chunk and wood chunks with a S at the very end. We can't use the square brackets because while they allow us to say the lowercase s or the capital S, they don't allow us to say S or nothing. For this, we use the question mark, which means the preceding character or nothing. For example, in the first example, for example, in the first set, the color, a question mark is there before the letter R, which means optional previous character. Does the words color with a U in it and a color with no U in it, both of them gets matched. Now the star is known as the Kleene star. The set of operators that allow us to say things like some numbers of A are based on the asterisk or the star. The Kleene star means zero or more occurrence of the immediately previous character or regular expression. So A star means any string of zero or more A's. This will match A or a multiple number of A's, but it will also match of minor since the string of minor has zero A's. So the regular expression for matching one or more A is A star, meaning one A followed by zero or more A's. More complex patterns can also be repeated. So an expression like AB in square brackets and then a star means zero or more A's or B's. This will match strings like AA or AB or simply BB. So in the second example, as you can see, the star is placed right after O, the second O. So it means zero or more of the previous character. That is, it will match all of the following that is given in the example. Sometimes it's annoying to have to write the regular expression for digits twice. So there is a shorter way to specify at least one of some character. This is the Kleene plus, which means one or more occurrence of the immediately preceding character or regular expression. Thus, the expression 0-9 in square brackets plus is the normal way to specify a sequence of digits. There are thus two ways to specify one or more characters. The first way is to say A star in square brackets or just A plus. We can think of the question mark as meaning zero or more one instance of the previous character. That is, it is a way of specifying how many of something that we want, something that is very important in regular expression. For example, consider the language of certain C, which consists of strings that look like the words that are given in the fourth example. One very important special character is the period symbol. It is a wildcard expression that matches any single character, except for a carriage return. Thus, in the example, beg.n, it will match any character between beg and n. That is, it will match the following things that are listed down in the example. The wildcard is often used together with the Kleene star to mean any string of characters. Now let's look at a simple example. Suppose we want to write a regular expression to find cases of the English article the. A simple but incorrect pattern would be just writing the word the as mentioned in this example. One problem is that this pattern will miss the word when it begins a sentence and hence a capitalized the. This might lead us to using the following regular expression. That is that as a lowercase t and a highercase t in the square brackets. But we will still incorrectly return text with the embedded in other words. Example, other or theology. So we need to specify that we want instances with a word boundary on both sides. That is, we will use the final regular expression as mentioned over there. But there is still one more problem with this pattern. It won't find the word the when it begins a line. This is because the regular expression, that is the first, that is the one highlighted in blue, which we use to avoid embedded instances of the, implies that there must be some single character before the. We can avoid this by specifying that before the, we require either the beginning of the line or a non-alphabetic character. The process we just went through was based on fixing two kinds of errors: the false positives, strings that we incorrectly matched, like other or there, and the false negatives, string that we incorrectly missed, like the higher case, the. Addressing these two kinds of errors comes up again and again in implementing speech and language processing system. In NLP, we are always dealing with this kind of errors. Reducing the error rate for an application often involves two agnostic efforts. That is, increasing the precision, which implies minimizing false positives, and increasing the overall coverage or the recall, which means minimizing false negatives. Now, in most cases, the false negatives affect the system in a much more varied way than the false positives. So importance must be taken in increasing the recall or minimizing the false negative as a first set of rules in developing a NLP system. Thus, as a summary, regular expressions play a surprising large role. Sophisticated sequence of regular expressions are often the first model for any text processing system. For hard tasks, we use machine learning classifiers, but regular expressions are still used for pre-processing or as features in the classifiers. They can be very useful in capturing generalization. Now let's look at the example of Eliza. Substitutions and capture groups are very useful in implementing simple chatbots like Eliza. Eliza, one of the most important historical NLP systems, was created by pioneering AI researcher Joseph Weissenbaum in 1966, and simulates a Rogerian psychologist, a kind of therapist who emphasizes mirroring back what they hear. Eliza is a surprisingly simple program that uses pattern matching to recognize phrases like "I need X" and translate them into suitable outputs like what would it mean to you if you get X? This simple technique succeeds in this domain because Eliza doesn't actually need to know anything to mimic a Rogerian psychotherapist. This is one of the few dialogue genres where listeners can act as if they know nothing of the world. Here's some fragment from a sample conversation with Eliza in 1966. Eliza's mimicry of human conversation was remarkably successful. Many people who interacted with Eliza came to believe that it really understood them and their problems. And in very precise and in very pioneering early work, Weissenbaum pointed out that the ethical issues in this attribution of human qualities to an artificial agent. We will return to this issue in the dialogues lectures. Eliza consists mainly of a series of substitution patterns, with some control for deciding what pattern to select, and some higher-level dialogue structure that we will come back to. Here we can see examples of capture groups for capturing the adjectives of user rights to describe themselves, and simple patterns for asking more details when the user uses generic statements containing all or always. Let's continue our study of basic text processing methods. In this lecture, we'll talk about some basic properties of words. How many words are there, and what are the properties of corpora? That's the plural of corpus, meaning bodies of text. Let's start by asking how many words are there in one sentence. Here's the sentence. I do a mainly business data processing. How many words are there in this sentence? It's a complicated question. Is a word? What about the cutoff main? In the first time I started to say mainly. We call things like main here as a fragment, and we call and field pauses. So for certain applications like speech applications, we might want to be counting this. Or how about cat and cats in this Dr. Seuss sentence? It will help to produce the distinction between a lemma and a word form. Two words are the same lemma if they have the same stem, the same part of speech, the same sense, whereas word form is the exact surface form of the word with all its inflections and endings. So if we are counting lemmas, cat and cats count as the same lemma. If we are counting word forms, cat and cats are different. Let's look at a part of another sentence. How many words are there in this sentence? Pause the video and count for yourself. Again, it depends on how you count. We could count word types, the number of unique words that occur in this sentence. By that count, we only count the once, even though it appears twice. Word tokens, we are counting every word token on the page. So the two does count twice. And what about San Francisco? One word or two? How about the and there? Different word form, same lemma. Again, it depends on our goals. And it's very important to make that clear whenever you report word counts. In general, we'll refer to the number of tokens with capital N. And we will use capital V to mean vocabulary, the set of all words. So the cardinality of V is the size of vocabulary, the number of word types. Although sometimes for simplification, we will just use the capital V to mean the vocabulary size when it's not ambiguous. There is a relationship between these two types of in running text called Heap's law or Hardin's law, which is that the size of the vocabulary grows with something over the square root of the number of word tokens. So a large corpus of n words, you can expect to see n to 0.7 word types. Here are the numbers of some common corpora. The switchboard corpus of phone conversation has 2.4 million word tokens, and there's 20,000 word types in those 2.4 million word tokens. Shakespeare has just under a million word tokens. Shakespeare is a quite small corpus. He wrote 800,000 words in his lifetime. And in that less than a million words, he actually used 31,000 distinct words. So he had a very, very broad vocabulary famously. And if you look at a very huge corpus, the Google Ngram corpus, that has a trillion different tokens, a very large number of words there, 13 million types. So how many words are there in the English language? Well, if you look at a conversation, 20,000 different words. If you look at Shakespeare's 30,000 words. And if you combine the two, probably somewhere not quite the sum of the two, but some larger number. But if you look at the Google Ngram, we have 13 million. And of course, some of those are probably URLs and email addresses. But even if you eliminate all of those, the number of words in a language is very large. Maybe there's a million words of English language. So where did this corpora come from? These characteristics of a text influence properties of the text. So is the text produced by a specific writers at a specific time, in a specific variety, in a specific language, for a specific function? For example, what language is a text in? As we'll see when we get to talking about what tokenization, what counts as a word can be different in different languages. Because language is so situated, when developing computational models for language processing for a corpus, it's important to consider who produced the language, in what context, and for what purpose. How can a user of a dataset know all these details? The best way is for the corpus creator to build a data set or a data set statement for each corpus. The dataset specifies the properties of a dataset, the motivation, why was the corpus collected, by whom, who funded it, the situation, when and in what situation was this text written or spoken. For example, was there a task? Was the language originally spoken conversation, edited text, social media conversation, monologue, or a dialogue? The language variety, what language was the corpus in? Speaker demographics, what was the age, gender of the authors of the text? Collection process, how big is the data? If it is of a subsample, how was it sampled? Was the data collected with consent? How was the data pre-processed and what metadata is available? The annotation process, what are the annotations? What are the demographics of the annotators? And how were they trained? How was the data annotated? And the distribution. Are there any copyright or any intellectual property restriction? In summary, when you study a text in corpora, it's important to be explicit about what you mean by word, that is a type or token, lemma or word form, and what are the properties of the corpora, their genre, the language variety, who wrote them, and how were they collected. In the next few lectures, we'll introduce text normalization, the process of turning a text into standard formatting of words or sentences. We'll start by thinking about how to break up this text into word tokens. So most standard tokenization programs for English or languages with similar writing systems need to deal with each of these issues. Here is a simple Python tokenizer in the natural language toolkit that has little regular expressions for dealing with hypotheses and currency and whatnot. But wait, what about all the languages that doesn't have spaces? Like many languages like Chinese, Japanese, or Thai, they don't use spaces to separate words. How do we decide where the token boundary should be? Chinese words are composed of characters called Hanzi, or sometimes just Z. Each one represents a meaning unit called a morpheme. Each word has on average 2.4 of them, but deciding what counts as a word is complex and not agreed upon. So in Chinese, it's common to use each character Z as a token. So the segmentation step is very simple. In other languages like Thai or Japanese, more complex word segmentation is required. The standard algorithms for neural sequence models trained by supervised machine learning. Word tokenization is an important step in text normalization. Here we introduce some common baseline methods, space-based and character-based tokenization. In this lecture, we introduce the byte pair encoding, or the BPE algorithm, that uses corpus statistics to decide how to segment a text into tokens. Another option for text tokenization, instead of using white space or single character tokenization, use the data that to tell us how to tokenize. Subword tokenization, because tokens can be parts of words as well as whole words. Three common algorithms are there for subword tokenization: the BPE, or the byte pair encoding, the unigram language modeling tokenization, and the word piece. All have two parts: a token learner that takes a raw training corpus and induces a vocabulary, a set of tokens; a token segmenter that takes a raw text sentence and tokenizes it according to the vocabulary. Now let's look at the BPE token learner. Let the vocabulary be the set of all individual characters. This is the initial set of the vocabulary. Now we'll repeat the following steps. Choose the two symbols that are most frequently adjacent in the training corpus, say A and B. Add a new merge symbol AB to the vocabulary. And finally, the last step is to replace every adjacent AB in the corpus with the combined AB. We'll run this step until K merges have been done. This is a basic pseudo program of the BP learning algorithm. As you can see, it does all of the three steps as mentioned before. The first step is to initialize a set of tokens in the character. And the second step is to make new token by concatenating and then update the vocabulary. And we'll do this until K times, and then after that, we'll update the corpus. And finally, we'll return the finalized set of tokens in the characters in the corpus. Most subword algorithms are run inside space separated tokens. So we commonly first add a special end of word character symbol before space in training corpus. Next, separate into letters. Let's look at the BP token learner in a better way. The original corpus, as you can see, is highlighted in blue color. Add end of word tokens resulting in this vocabulary. So the first step is to find which is the most frequent adjacent characters. As you can see in this example, E and R are the most frequent. So we'll combine E and R to merge as a symbol called ER. And then we will add it to the vocabulary as shown in the next step. After that, we'll replace all of the occurrences of ER in the corpus with the new symbol ER, as shown in the last example. After that, I will again run this step in K times. So as you can see, ER followed by a space is the second most frequent symbol. So we will add a new symbol ER space in the vocabulary and again replace that symbol with the previous occurrences in the corpus. We will continue this again to find out what is the next frequent character, addition character. As you can see, N space N and E are the next most frequent adjacent characters. So we will replace this NE with a combined symbol NE in the vocabulary and also in the corpus. The next merges are as follows. As you can see, after the final merge, a vast vocabulary has been created, which are the tokens in the corpus. Now let's look at the BP token segmental algorithm. On the text data, run each merge learned from the training data greedily in the order we learned them. So merge every ER to a symbol ER, then merge ER space to ER space, etc. The result is as follows. In the test set, new word with a space would be tokenized as a full word. The test set lower with a space at the end would be tokenized, would have two tokens, low and ER space. The properties of the PE tokens usually include frequent words and frequent subwords, which are often morphemes like EST or ER. A morpheme is the smallest meaning-bearing unit of a language. Unlikeliest has three morphemes, un, likely, and est. The byte pair encoding algorithm we have described is one of a set of corpus-based tokenizers that together are now extremely commonly used throughout NLP. Now let's discuss how to put all words in a standard format, a process called word normalization. We'll also talk about sentence segmentation, the process of breaking up your text corpus into larger units called sentences. What is word normalization? Putting words tokens in a standard format, that is u.s.a is similar to USA, and FED with the F capital is similar to FED with lowercase f, and M, is, B, and R, they are the same. Applications like image recognition reduce all characters to lowercase, since users tend to use lowercase. Possible exceptions, uppercase in mid sentences like General Motors or sale. For sentiment analysis, MT, information extraction, case is useful. There, US versus us is important. Lemmatization. It represents all words as their lemma, their shared root, that is a dictionary head word form. For example, am, are, and is have the same lemma be. Car, cars have the same lemma car. For example, in the sentence, he is reading detective stories. If we do lemmatization on this sentence, it will become as he be read detective stories. Lemmatization is done by morphological parsing. Morphemes, the small meaningful units that make up words. Stems, the core meaning-bearing units. Affixes, parts that adhere to stems, often like grammatical functions. Morphological parsers, parse cats into two morphemes, cat and s. So if we do stemming in a very crude way, of the text shown in the left, the result will be the text shown in the right. As you can see, this does not conform to the idea of a simple English language, but this is very useful in natural language processing, which will be shown in the next few lectures. Into about string similarity. Now let's look at edit distance. Edit distance gives us a way to quantify how similar are two strings. More formally, the minimum edit distance between two strings is defined as the minimum number of editing operations like insertion, deletion, substitution, needed to be performed for transforming one string into another. Much of natural language processing is concerned with measuring how similar two strings are. For example, in spelling correction, the user typed some erroneous string, let's say graph, GRAFFE, and we want to know what the user meant. The user probably intended a word that is similar to graph. Among candidate similar words, the word giraffe, which differs by only one letter from graph, seems intuitively to be more similar than, say, grail or graph, which differs in more letters. Another example comes from coreference, the task of deciding whether two strings, such as the following, say, Stanford president Mark Levin or the Stanford University president Mark Levin, are the same or different. Again, the fact that these two strings are very similar seems like useful evidence for deciding that they might be coreferent. In computational biology, we align two sequences in the following manner. The resulting alignment is shown below. So the edit distance can also be used to check the alignment of two strings. Also, for machine translation, information extraction, speech recognition, edit distance is very, very important. The minimum edit distance between two strings is the minimum number of editing operations, insertion, deletion, or substitutions needed to be performed to transform one string into the other. Two string and their alignment. For example, in this image shown, this intention and execution are aligned. As you can see, the first letter is not present in the second string, and the fifth letter C is not present in the first string. So it is here where the edit distance comes into action. It is much easier to see this by looking at the most important visualization of string distances, an alignment between the two strings. Given two sequences, an alignment is a correspondence between substrings of the two sequences. Thus, we say I aligns with empty string N and E and so on. Beneath the aligned strings is another representation, a series of symbols expressing an operational list for converting the top string into the bottom string. D is for deletion, S is for substitution, and I is for insertion. We can also assign a particular cost or weight for each operation. The Levenshtein distance between two sequences is the simplest weighting factor in which each of the three operations has a cost 1. We assume that the substitution of a letter for itself, for example, T for T, is 0 cost. The Levenshtein distance between intention and execution is 5. Levenshtein also proposed an alternative version for his metric, in which each insertion and deletion has a cost of 1, and substitutions are not allowed. This is equivalent for allowing substitution, but giving each substitution a cost of 2, since any substitution can be represented by one insertion and one deletion. Using this version, the Levenshtein distance between intention and execution is 8. So how do we find the minimum edit distance? Searching for a path sequence of edits from the start string to the final string. The initial state, the word we are transforming, operators, insert, delete, or substitute. We'll also have the goal state, the word we're trying to get, and the path cost. What we want to minimize is the number of edits. We can search the entire corpus for minimum edit distance, but the spaces for all edit sequences is huge. We can't afford to navigate naively. Lots of distinct paths wind up at the same state. We don't have to keep track of all of them. Just the shortest path to each of those revisited states. Let's define the minimum edit distance. Say we have two strings x of length n and y of length m. We define the minimum edit distance d ij, the edit distance between x and y. That is the first characters of x and the first j characters of y. The edit distance between x and y is thus d in brackets m comma n. Now, how do we find the minimum edit distance? We can think of it as a search task, as mentioned previously, but it will be a huge computational work to have to search the corpus naively. The space for all possible edits is enormous, so we can't search naively. However, lots of distinct edit paths will end up in the same state. So rather than recomputing all those paths, we could just remember the shortest path to a state each time we saw it. We can do this by using dynamic programming. Dynamic programming is the name of a class of algorithms first introduced by Bellman in 1957 that apply a given table-driven method to solve problems by combining solutions to subproblems. Some of the most commonly used algorithms in natural language processing make use of dynamic programming, such as the BTB algorithm and the CKY algorithm for parsing. The intuition of a dynamic programming problem is that a large problem can be solved by properly combining the solutions to various subproblems. Consider the shortest path of transformed words that represent the minimum edit distance between the strings intention and execution. Imagine some string, perhaps it is execution, that is in its optimal path. The intuition of dynamic programming is that if execution is in its optimal operational set, then the optimal sequence must also include optimal paths from intention to execution. Why? If there were a shorter path from intention to execution, then we could use it instead, resulting in a shorter overall path, and the optimum sequence wouldn't be optimum, thus leading to a contradiction. The minimum edit distance algorithm was named after Wagner and Fisher, but independently discovered by many people. Thank you for listening to today's lecture. If you have any question, please feel free to drop me an email.